So everybody, I'm David. I'm an architect responsible for Proofpoint's cloud security products. And I've been doing stuff with data for pretty much my entire career in the industry, which is almost 24 years now. So before I start, let's do a quick survey. Who here has been working in the industry for 5 years? At least 5 years. Yeah, almost everybody. How about 10 years? 20 years? More than 20 years? Well, I feel old. Okay, good. So you'll have a lot of interesting stuff to find out. And so most of this conference is about talking about things that are on the bleeding edge of what we have today in the industry, very new tools, new techniques, which is very cool. And that's how it should be. And I thought it would be actually pretty cool to go back in time and talk about the things that brought us here and gave us all of these cool tools. And as you'll see throughout this session, most of the stuff we take for granted today has actually been invented 30 or 40 years ago as a result of business needs, right? So pretty much most of what we do is a result of economics. There's a business need, we can find a way to do it optimally and cheaply, and then we create a new technology and optimize it over time, right? And so before we get into all of that, as most of you know from going to big data conferences, there's exactly 2 jokes you're allowed to tell about big data. The first official joke, of course, is a large picture of Lieutenant Data, right? Which is what I go for, obviously. And that one is very funny. And the second official joke is a quote from a post on Facebook by psychologist Dan Ariely in 2013, which talks about how big data is like teenage sex, in which everyone's talking about this, everyone thinks everybody else is doing it, and no one actually does it very well. And I kind of stopped using this joke anymore because the thing is, it's not really funny, right? Because everyone actually is doing big data. Just look around. And we're actually pretty good at big data right now. And so this joke kind of fell out of use. And so officially, there's really only one joke you're allowed to tell about big data. And so since we're all doing big data, let's talk about what it actually means. And originally, the founding of big data goes back all the way to the 70s. Because if you go and you read a lot of blogs and you look at technical talks, you might get a feeling that we invented this idea that you can use data to get value out of it in the last 5 years. Because every blog is like, how we use big data to bring out value in the insurance industry. Well, no, not really. Right? Smart people have been using data to get value for the past 50 years, pretty much as long as we had databases, even before that. And so really, the original need was to run analytics and get value out of data. And if you look about it, so this slide is a very famous slide. It first showed up in a blog called The Big Data Value Continuum by Scott Carr, who is the founder of VaultDB. And it was very popular for a while at conferences around 2013, right? And this actually shows something very important about the way we look at data. The value of data isn't constant. The value of data changes over time, and it really depends on how much data you're actually looking at. And intuitively, I think most of you kind of feel this, right? Because I think like half the people in this audience do something with fraud detection in real time. So you can intuitively think, well, if you have a fraud event or some kind of event, and you look at one item of data, doing something with it very quickly has a lot of value for your customers. Waiting 24 hours to do the same thing with that data probably has less value. And so the value of a single item decays over time. And this is where most of the stuff we do with fast databases, operational data stores, and more stream processing it comes in. When you look on the other side of the data value continuum, the more data you look at in aggregate and the longer time frame you look at, the more value you can extract out of the aggregation of data, right? Which means looking at a long history back can give you bigger trends, can give you actually much more valuable look back than trying to do data aggregations on 5 minutes worth of data, right? And this kind of makes sense intuitively. And if you think about it, this pretty much dictates most of the data architecture we use in the industry, right? If we do a survey, I think most people here work on some kind of system, which is a form of Lambda architecture. It has some kind of real-time stream. It has some kind of batch layer, and it uses both of those to actually get value and combine them together, right? So actually, let's do a quick survey. Whose production system is some form of streaming and batch Lambda architecture? Yeah, that's pretty much what I figured. It's most people here. And there's a good reason for it, because you want to extract value out of data in every way possible, right? If you want to succeed in business. And so most of the technologies we are going to talk about kind of fall into one of these two categories. They're either trying to get data out of value out of data very quickly with individual data items, or they're trying to store a whole bunch of data and get value out of all of that in aggregate. And the problem with that, with the second approach in aggregate, is that getting value out of data in aggregate is extremely expensive. Now, if you think about this query, and this is your typical canonical analytics query, I've spent the last 24 years writing and optimizing different versions of this exact query, right? You go and you select some data items, and from a join of several tables of facts and dimensions, and you group it by something, times, and add campaign IDs or countries or something, and then you subselect for some population, like number of users, right? And this query has pretty much driven analytics for the past 40 years, right? Ever since we invented query languages. And if you think about which parts of this query are actually expensive on aggregate, well, let's think about it. Aggregations on large amounts of data, very expensive, especially if you don't have tricks with indexes and statistics. Aggregations are ridiculously expensive. How about joins? Are joins expensive? Yes, joins are notoriously expensive, especially in distributed systems where you have to shuffle data around the network and all that stuff. It gets very complicated and exponentially expensive. How about grouping and shuffling data? Ridiculously expensive, right? Again, especially in distributed systems where you have to shuffle data between workers and all that. And the last part, subselecting a smaller part of your total data. That messes up with caching. It's very hard to do. It's a separate query. Pretty much every single part of this query is expensive and difficult to engineer, right? And this is why we spent pretty much the last 40 years building better and better technologies to optimize different parts of this analytics query, right? And which parts did we optimize? Well, initially, all we had was even non-relational databases in the early 70s. At the end of the 70s, a guy by the name of Edgar Codd, who contributed hugely to the whole field of relational databases, actually came up with the idea of relational databases, right? He published what's something called the 12 rules for relational data stores, which was hugely influential in the industry. He worked for IBM at the time. He contributed to the first IBM databases. And somewhere around the early 80s, this idea that you could take data from different databases in the organization. And in the 80s, databases weren't a file you install on the PC, right? There were massive mainframes with proprietary data systems, right? My first job in databases was liberating data from one proprietary database at Intel and then locking it back up into a different proprietary database. And so taking the data from multiple data stores and joining them for analytics was an actual physics problem, right? How do you liberate data from one database with one weird schema into a different one and join them ideally, dynamically, not once every year. And so this paper that I have on the slide is one of the primary scientific papers on the topic. It popularized the idea of what we today know as the enterprise data warehouse. They talked about the business data warehouse, which is this idea that you can use ETL processes to bring data from different parts of the organization, from different databases, into one massive, ginormous database on presumably a huge, expensive mainframe, and store it historically. Store as much of it as you can afford, pretty much, and categorize it and have a very well-structured schema. And then once you bring all the data from different databases into this one warehouse, then you can run the kind of analytics queries that require joins and all that. Didn't make the joins more cheaper, but at least it made them possible, right? And so everything we know about data warehouses and data lakes that we have today, all of that actually started as this business idea of let's take a bunch of different data sets, put them in one place, and then run analytics on them, right? Which today seems trivial. Obviously, everyone's doing it. Like there's like 50 different cloud databases you can choose. But this paper pretty much launched it. Like if you look at the number of citations, and for those who are lucky enough never to deal with academia, citations are kind of like retweets, if you want to talk about, but for academics, right? So the more citations you have, the more other academic papers cited your paper, right, and referred to it. And it's kind of like a big prestige measuring metric, but also this paper is hugely popular. The next big jump in what we can do with data came in the early 90s, again, from a paper by Edgar Codd, the same one from the relational databases. And he proposed this idea of using OLAP, online analytical processing databases, to take data and pre-generate and pre-compute all the different possible aggregations and data slices in advance in order to achieve better performance with aggregations and grouping. Today, I think everybody knows what all-up cubes are. Has anyone actually used an all-up cube? There's a huge Druid community in Israel, right? And Druid is like the great-great-great-grandchild of essentially this academic paper, which is even more influential and more highly cited than before. And this idea of all-ups is you load a bunch of data with a complex ETL process into one data store, and then you pre-compute all of the possible aggregations you can think of, and then you expose that, which solves two of the really expensive parts of that analytical queries we looked at, but forces you to give up a lot of flexibility, because you kind of have to know in advance everything you will ever want to query, because if you want to change your mind, you have to rebuild the whole all-up cube pretty much from scratch, right? And today, obviously, we have much better technologies which kind of do it for us and more real time. But in the early 2000s, I was working still at Intel, and we had a process which would every night take a bunch of data, ETL it into a all-up data store. That was right about when Microsoft came out with Microsoft Analytics Service, which is a separate technology company they purchased and then rolled into Microsoft SQL Server. And it would run an all-up cube combination if the ETL succeeded. And it was about 50-50 every night whether the ETL succeeded or not. And so every morning we would come in and take bets on whether we're going to do any work that day, or we're going to be basically fixing the ETL and running the all-up computation again, which took 12 hours. Which means if we messed up the ETL process, nobody did any work that day at all. And so we're talking about databases. Obviously, the next logical step is to maybe try to get a bit more use out of your normal database. Before we go into some special super analytics store with a bunch of data in it, can we make our normal database, our operational database, a bit faster so it can sort of take some of the same use cases as analytical databases simply by brute strength, and also support the other side of the data value chain, which is real-time, doing something in real-time with data. And of course, that brings us to NoSQL. Now, NoSQL is actually much older than anyone here probably realizes. The first use of the word NoSQL comes from a database that was created in 1998 by a software developer named Carlos Strozzi. And he essentially took a relational database and changed the query language from SQL to something else. He called it NoSQL. This is the actual web page for the NoSQL database. You can go and find it online. You can download the source code and look at it. It still exists. Now, this database, of course, is nothing like the NoSQL databases we all think of today, right? So the way we think about NoSQL comes from a much later event. This is an invitation for a meetup that happened in 2009. And this is the first use of the word NoSQL the way we use it today, right? And if you read the agenda for the meetup, you'll find a bunch of interesting and well-known names. For example, you can see that at 10:40, Jay Kurtz, the Jay Kurtz of Kafka fame, one of the founders of Confluent, gave a talk about Voldemort. And there's a talk about Cassandra and HBase and a bunch of names you should recognize. CouchDB later morphed into Couchbase. I worked at Couchbase. So this event pretty much popularized the term NoSQL in the industry in the sense that we understand it today. And pretty much the entire NoSQL movement came out of this event, right? So NoSQL, as we understand it, is pretty old, right? And it's actually not coincidental that this happened in 2009. That's the time when a lot of the interesting technologies we use today kind of got their first iteration or first start, right? So if we think about what else happened around that year, we naturally go to the thing that most of us actually really use, which is data lakes and Hadoop. Now, the word data lake didn't come about until 2010. It was actually coined by the CTO of Pentaho, which is a company that makes BI tools. And he used it in a conference and in some blogs, and it kind of spread around. And so the idea of this data lake was kind of new. But before we can talk about data lakes, let's talk about Hadoop itself. And Hadoop came about in about 2002, when two developers named Doug Cutting and Mike Caffarella were working on something that's known as the Apache Nutch project. It still exists today. It's a web crawler. It's an open source web crawler you can use. At the time, they were trying to get this project to index 1 billion pages. right? Which, when you think about 1 billion pages, what's indexing 1 billion pages? It's not like Dr. Evil going 1 billion pages, right? It's actually not a lot, right? I mean, our system deals with 1 billion event every day. We store a year worth of events. It's kind of expensive, but it's definitely doable. But we're talking about 2002. That's almost 20 years ago. And so in 2002, indexing 1 billion web pages, they estimated would cost roughly $500,000 in hardware and around $30,000 in monthly maintenance cost just for the hardware, right? Which is ridiculous at the time. Luckily for them, in 2003, Google released one of their first really famous white papers about the Google file system, which is a distributed file system that runs on a redundant array of commodity hardware. And it's a massive change in the way we think about storing data. And a year later, Google released another very famous white paper about MapReduce, which is it's the simplified algorithm for processing big data on large clusters. So taking the lessons from those two papers, Mike and Doug rebuilt the entire Nudge project from scratch, and they actually launched a new project, and they named it, can you guess? You don't need to guess, they named it Hadoop. I'm pretty sure everyone knows the elephant picture. The name Hadoop actually comes from a stuffed elephant toy that Doug's 2-year-old son had, and they checked, according to story at least, they picked it because simply it was a unique sounding word that was easy to pronounce, and it didn't have any major web search hits at the time. And so the name kind of stuck. And in 2006, by then they were working at Yahoo, they actually built a system that had up to 1,000 nodes of Hadoop, and they could easily index the 1 billion pages they aimed for. In 2007, version 1.0 of Hadoop was actually officially released. And from then, it spawned into a massive amount of ecosystems and other tools. I'm pretty sure everyone uses at least something that kind of came out of this idea of using data storage that's decoupled from the data processing and storing data on a redundant, highly distributed array of storages, and then putting the compute somewhere else. And the really major ideas that came out of it all happened in the area of 2009 to 2012, which, if you think about the economics of it, was pretty much around the time most of the big tech companies, your Googles, your Facebooks, LinkedIn, really had the need to analyze huge amounts of data, and the importance of real time between mobile apps and web apps and all that. The importance of actually processing data in real time was paramount, which brings us to real time. And when you talk about real time, you have to talk about stream processing, which is actually, again, a much older idea than what we think. Stream processing actually gets its start in the early 90s in what's called active databases. Those of you who actually dealt with SQL and relational databases know that there are databases used to have triggers. They still have, right? But today we think about database triggers kind of like an anti-pattern, sort of like using singletons or having global variables, which means everyone still does it, but they feel bad about it, right? And so using triggers in databases is kind of not a cool thing anymore. But at the time, adding triggers to data change events was a huge, huge innovation, right? And from that, the idea of you can actually run user-built code on top of data events, and then later on, the next iteration of that would be to take the stream of events, put it outside of the database, and run your user code on that stream of change events was a massive innovation, right? And so this idea of stream processing kind of split into separate branches. The first branch was complex event processing, which is still in use today, mostly in insurance, banking industries. And the idea of complex event processing is not to look at a single data event, but to look for patterns of events in a stream, right? So match, for example, someone filing for bankruptcy and 2 days later filing an insurance claim, and then 2 days later going on a cruise, right? And you match those events and you say, well, that's insurance fraud, right? And today we still use a lot of that in pretty much what half the room I think here does, right? Fraud analysis, all that, except we don't really use complex event processing frameworks anymore. We use something else. But this is the first project I could find that actually had a real working CEP. It's the RAPID project from Stanford. This was developed in 1996, and the web page still exists. You can actually go and look at the project in all its 90s HTML design glory. This looks exactly like something I designed in high school. And so that is kind of not really mainstream today unless you're working in banking and insurance. What is mainstream, and I'm pretty sure familiar to most of you, is actual distributed stream processing, which is, if you think about it, remember the analytics query we had at the start where you take a bunch of data and aggregate all of this? Around the year 2010, suddenly we had this idea that, yes, we can do this query, but what if we did it in real time? Because we want to know the answer now. We don't want to wait 24 hours for the Hadoop job to finish. And so this idea of actually taking analytical queries and converting them to run on a stream of data in real time, again, very, very radical idea. But ultimately, today you can do that. You have stuff like Kafka SQL and a bunch of other frameworks where you can actually have your analytics query and run it on a stream of data and get intermediate results. And the very, very first distributed stream processing project that's built in the sense of we think today, which is a direct acyclical graph of stream processors. So you have a bunch of classes or pieces of code, and you run events through the pieces of code, and each one acts on every event. The very first project that was actually successful is called the Aurora project, which was a collaboration by Brandeis, Brown, and MIT. It was a pure research project. It didn't actually go into anywhere in the industry. They tried to follow it up with the Borealis project because scientists like puns. And that project got a little bit of commercial support, but really didn't go anywhere in 2005. And really the first successful stream engines showed up in the year 2011. And 2011 was a huge year for stream processing, right? This is the year most of the big stream processing frameworks that we still use today kind of started, right? So Kafka was released in, I think, January 11, version 1 of Kafka. Flink was released in May 2011, and Storm was, the first version was released, if I'm not mistaken, around August or September 2011, right? So in almost around half a year, in the same year, different companies had the same business need, and the engineering at the time was at a level where it was possible and economical to build something that takes a bunch of data and runs it through a stream processor in real time, right? And today we use either exactly those technologies, obviously much more advanced versions, or something that came from them, right? Today we don't really use Storm as much. It kind of morphed into first Trident, then Heron and stuff like that. And Flink is still around, and actually Flink has a really cool CEP module if anyone wants to use it. And Kafka then built Samza to run stream processing on top of that, and then Kafka streams and so on. And today at Proofpoint, for example, pretty much everything we have is built on Kafka streams. And so that is almost 10 years ago, slightly more than 10 years ago, when we actually got real stream processing. Now, if you think of the other side of the data value chain, the equivalent to stream processing also happens pretty much around the same time for exactly the same need, because most of us want to get value out of data, both on the real-time side and on the aggregation side. And so the engineering expertise that was needed to build both of those kind of occurred around the same time. So Hadoop came about in 2002, but it wasn't until 2010 or so that this idea of actually building a data lake that came about, right? And the data lake, if you think about trends in engineering, usually the first version of technology to solve a particular problem comes with a bunch of restrictions. If you think of programming languages, statically typed languages are very restrictive and they do a specific job, and they let people use the language easily. And then usually a couple of years later, someone comes along and says, all this stuff doesn't work for me. I don't like static types. I want to have no types or 50 types or whatever. And then they build, Perl and Python and other weird languages. And then a few years later, someone comes along and says, stop fighting, right? Let's have both of those. And they build something like Scala, which has, a bit of both. And this is true for databases as well, right? We had relational databases, very restrictive schema. The first data warehouses were built on this idea of strictly categorizing data, very tight schemas, very hard to actually change and migrate. Anyone who's ever done schema migrations in SQL knows what I'm talking about. And then, about a decade later, someone comes along and says, we don't need schemas. Schemas suck. Let's build those SQL databases with no schemas. And, who needs ACID guarantees? We'll just give up a bunch of features and we gain a bunch of flexibility. And then, a few years later, someone comes along and says, stop fighting. It's okay. We can have both, right? And we can get like new SQL databases, which kind of have ACID guarantees and they have distributed and highly resilient systems and scale and everything you have. And this kind of thing happens over and over if you look at tech, right? So if you look at large data storage, first we had data warehouses, and then someone came along and said, you know what, all this data warehouse stuff and ETL, We don't like it. What we're going to do is we're actually going to put all of our data in this giant file, and whenever we need something, we'll just look through the entire file. It's fine. And if you think about it, like, without the sarcasm, the economics of it is very important, right? Because comparing enterprise data warehouses to data lakes is purely a question of economics. In normal databases and data warehouses, you pay at the point of ingestion. You take your data, you do a lot of work on it, you index into a database, you pay all of the compute up front, and then querying it is actually very cheap because you organize the data to be easily queryable. And so the cost of storing data in databases, especially relational databases, is continuous. You pay a lot up front, and then you continue paying the maintenance cost for the compute of the database. The idea of a data lake is to switch it on its head, right? When you have enough data and you don't query it very frequently, it actually makes it much cheaper to store all of this data as quickly as possible. Just compress it, put it in a big file, have a file system which can actually let you store the data and not lose it. And then whenever you need to run the query, then you can just brute force it, run over all of your data. Of course, today we have a bit of both, right? If you look at modern data cloud systems, they have a bunch of stuff from the data lake, right? You can put a bunch of files on S3 or HDFS, but you don't just put text files there, right? You put columnar formats, you help the data framework actually find the data you want to need. And then when you run queries, you pay a lot at query time, right? It's not optimized to the level of indexes and databases. And you kind of get a bit of both. And that idea pretty much came from the combination of data warehouses and data lakes in 2010 or so, right? And if you think about when most of the big SQL query engines came about, they all happened within the span of about 2 years, right? So Google had their internal Dremel tool, which is a query processing tool for running, getting data from different data sources and querying them all together, but primarily over flat file storage, which then turned into BigQuery, which is still everyone uses today. It's one of the most used data warehouse and technologies. The Hadoop project came up with Hive, which is a SQL language to run over HDFS, roughly around the same time. It's like 2 months apart. We got Apache Drill, which is an open source implementation of Dremel, and there's like 50 other technologies I couldn't really fit on the slide. But one of the bigger ones, which I'm sure a lot of companies here use, is Presto, which Facebook built for themselves to address exactly the same need, except someone there said, well, we don't need any of this Hadoop stuff because MapReduce sucks. So we're going to build our own MapReduce. Right, and so they built Presto, which is really a very cool technology and a good iteration on that. By the way, quick query. Who here has actually written a MapReduce job? I don't mean word count from the examples. I mean actual production MapReduce. Yeah, I didn't think so, because MapReduce sucks. But it was amazing at the time, right? But today, obviously, we don't want to write MapReduce. Like, the whole history of technology is a series of taking a hard problem, first solving it in a way that only appeals to engineers who like to write code and suffer through writing MapReduce, then build a level of abstraction on top of that. For example, with Hadoop, we got first query languages like Pig Latin, and a few others, which are not really SQL. Then build the next level of abstraction once the technology gets mature enough, and then you get languages like SQL, right? And then people who aren't pure software developers can use that, and analysts and data engineers, and then build the next level of abstraction on top of that, which is visualize and give data exploration and let people who are really not engineers but are analysts and data and business people access to the same data. And like every stream of technology you think of kind of goes through those steps. Even from databases to query languages to everything, start with something very bad and very cumbersome to use, but it solves the problem, and then you progressively go higher and higher from that. And I think the next jump, the big jump in technology that's going to happen today, this year, next year, is this move from monolithic architectures, data lakes, and big data pipelines to a more distributed model, right? And I'm very happy that the next talk after me here in this hall is going to talk about data meshes, which I think fits really well. I really think data meshes, which is this idea of actually, instead of building one monolithic data architecture, building a lot of micro data architectures and exposing data sets as products, the same thing we did with microservices 10 years ago, really is the next big paradigm in how we use data, because it continues the chain of steps of adding new levels of abstraction and making less and less, and make it easier to use your data to extract value out of it, right? And so, as we talked about, a lot of the technologies we really use today Started out as business needs in the 80s and 90s, turned into kind of research projects in the late 90s and 2000s, came up with very early versions by large tech companies in 2010 or so, over the course of about 2 years, then kind of went mainstream, and the rest of us started using them in 2013 and 14, and then a few years later, they kind of became commodity, because today every big cloud provider offers managed versions of pretty much everything we talked about today, right? So now that we learned a little bit of history, when we understand where we came from, let's spend the rest of the day learning about really cool, cutting-edge, new stuff in the industry. I hope you all enjoyed the conference. Thank you very much for coming.